Kinetics. So kinetics basically is telling you how fast a reaction happens. Thermodynamics, when we get to that, will tell us if the reaction can occur, whether it's spontaneous or not spontaneous. But kinetics will tell us how quickly the reaction occurs. So some reactions are thermodynamically favorable or feasible, but they happen so slowly that it's like they don't happen. And the very good example of that, which is, I might need to turn the lights off of this because that's not very easy to see. A very good example of this is, I don't have my lamps on. It's going to be really dark if I turn it off.
Do it.
If you have carbon in the form of diamond, thermodynamically it will actually degrade and go back to just straight up carbon or carbon monoxide. Okay, so when they say a diamond is forever, it's actually thermodynamically not, but it happens so slowly kinetically that essentially a diamond is forever. Okay, whereas when you have water and hydroxide or hydrogen hydroxide happens very quickly, so fast that it seems to be instantaneous because it's kinetically favorable. Okay, so thermodynamics tells you if it's thermodynamically favorable, kinetics tells you how quickly the reaction occurs. Okay, so that's the difference. So reaction rate is the change in concentration of a reactant over time. Okay, we will always signify concentration in those brackets, whether it's for solutions, whether it's for gases or whatever. That bracket always means concentration. Okay. And that's the rate for the product, change in product over time. Okay? If the reaction is involving the reactant, if you want to see the change in reactant over time, you put a negative sign in front of that change in concentration over change in time. Why the negative sign?
Because the concentration decreases.
Yeah, the concentration is decreasing as your reaction proceeds, right? Makes sense. Okay? So here's an example of the nitrogen dioxide decomposing, and you can see how the concentration of the reactant is going down as the concentration of the product is going up. That makes sense, right?
Say that part again?
If you look at the lines, the concentration of the reactant is decreasing.
The green.
Yeah, as the concentration of the two products are increasing. And at some point, they will reach equilibrium and level out. It just didn't take the graph far enough over. Okay? Most reactions don't go to 100% completion, so they reach an equilibrium stage. That's like 4 chapters after kinetics is equilibrium. Yeah, but I'm just saying they'll level out. We just didn't take the graph over far enough. Okay? The way that you can find these instantaneous rates is you can take the slope of the lines. Okay? That's how you can find the rate. Okay? We're not going to find them that way. We're going to do them a little different. Okay? But here we have this reaction. And in the experiment, we have oxygen gas forming at a rate of consumed at a rate of 0.036. What would be the rate of disappearance of N2O5?
What page is this on?
This is just a thought.
Oh, okay.
Yeah, it's not in the, yeah. Okay? This is just to help you through the thought process. So if the oxygen is decreasing at this rate, what would be your rate of appearance of N2O5? No, not the same. Look at the stoichiometry. It's a 1 to 2 relationship, right? So as the oxygen is disappearing, how quickly would the N2O5 be appearing? Twice as much. Twice as fast. So that's you do have to use the stoichiometry of that to see because of that. What would be the rate of consumption of the NO2?
4 times.
Yeah, it'd be consumed 4 times.
That is times 4.
Exactly. That's just, yeah, you don't have to do the math. It's just so that you're understanding the stoichiometric relationship.
144.
Wait, so NO2 would, what did you say, it would what, 4 times as fast?
Mm-hmm. Because you could literally take the 0.036.
Wait, but it would do what 4 times as fast?
Well, let's do the relationship. 1 mole of O2, 4 moles of NO2. So then you would get the rate of disappearance of NO2 would be 4 times.
Oh, so it would disappear.
Yeah. So it's still, you can use that mole ratio for the stoichiometric relationship can be used in almost anything. They started stoichiometry today in pre-AP.
Oh, for the first time, really?
Oh, actually early. We finished, we're actually we're a unit ahead in pre-AP. We have to be because we end so much sooner this year. Like, I had to move everything up, okay? To get the instantaneous rate, we can compute the slope of a line tangent to that curve. The rate is equal to the negative slope of the tangent line. Good news is we're not going to really do that. Just so you know that's how they get it, okay?
Well, we don't really have a winter bug.
Yeah.
It's up to a $200 fine.
All right, so here's how you can do that, get the slope, and it tells you the rate of the, at different times, okay? The rate at different times. The rate of the reaction is not constant, obviously, it's changing with time, but because that makes it difficult for our calculations, we're actually going to only be working with initial rates, so like at the beginning of the reaction. And we're going to assume that the reverse reaction is negligible for our initial rates. Okay? So, factors affecting the reaction rate. See that little space next to the graph? This would be a good spot to write this in. Okay? Factors that will affect the rate. Okay? Temperature, right? Why would temperature affect it?
Because it's more energy.
Yeah, we're speeding up the particles, more energy, it's going to happen faster, right? The nature of the reactants. Would you expect gases or solids to react quicker? Gases, absolutely. It's more, yeah. Concentration of the reactant. If we have a higher concentration, we're going to have a higher reaction rate. I'm going to pause the video while y'all are writing because that would just be a lot of...
So the bracket, if it's just a...
Okay, so those are the things that can affect your reaction rate. So let's go on. Well, it's going to let me go to this. This is a, so if you were in pre-AP last year, you saw this video. My seniors, I don't know if you saw this video, but it's just kind of a little fun little video. It's not going to let me do it. I have to do it from the, I have to do it from over here. It's called TED Ed.
Tim and Moby. And it was like brain.
Heart?
Like heart. When it popped in. It was like the robot. And the button looking down.
So this is kind of just a fun little thing to help you.
I think it's for anything.
Here you go.
Bit of history too. I can't hear.
So my juniors, we saw this last year. My seniors haven't, so I decided to show it again.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student, and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk her to class. And you'll never guess who went together to the dance later that year.
Tim and Moby is what happens every
Those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now, you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have 2 important characteristics. 1, correct orientation that allows books to be knocked from one's hands, and 2, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I propose 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I propose that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date to the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help make sure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small, and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased, and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? Then a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match.
Is that the catalyst?
Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing two particles together and orienting them correctly in space so that the two can meet at the correct configuration and allow a reaction to take place. So, to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.
That actually makes sense.
In a way, in a way it did.
They're not TED because they're,
That's like TED Talk, right?
it's TED Ed. They have, actually, they have, so they actually have a lot of topics on TED Ed, not just science ones. So if you want, like government or something like that, you can go there. Interesting turn. And just a fun way to kind of show that. Okay, so differential reaction rate laws is what we're going to be doing today. We'll be doing that today and tomorrow. The worksheet that you picked up today we'll work on in class tomorrow so you can ask questions. The differential rate laws are not too hard. They're pretty easy, okay? So and we did this in Chem in pre-AP. We did not do it in regular. We just talked a little bit about kinetics, but we did do rate laws in order of reactants. We didn't calculate them. I think we just gave them to you. I don't remember. It was a long time ago. So for this particular reaction rate, 2x plus y equals z, first of all, your products do not appear in your reaction rate. Okay, it's only your reactants. And then so you have rate is equal to k, which is a constant. It's called the rate constant. And then you would do the concentration of the reactant raised to the coefficient's power. So in this case, it would be m and n. So if we were going to write the reaction 2xy, we would actually say the rate based on that, without calculating, we could say is k, concentration of x raised to 2, concentration of y raised to 1. If we were just doing it based on the equation. Most reaction rates are determined by experiment, okay? But if they ask you to write the reaction rate based on just the balanced equation, that's how you would do it, okay? But most of the time they're going to be experimental, okay? So in this case, we would say for x, with the order of x is second order with respect to x. For y would be first order with respect to y, and then the overall reaction rate would be the two superscripts added up. So it'd be third overall. Okay, so we would say second order respect to x, first order respect to y, don't know how to spell respect apparently, and then third order overall. So that's how you read a reaction rate. Okay? All right? So this is what we just said. Go over it again. The orders are positive. They can be negative, or occasionally they can be a fraction, which is kind of freaks people out. Usually it's going to be a small positive whole number, but I do need to make you aware that occasionally you will have a fraction as an order. You can also have zero order. Yes?
Whenever you said it was like you combine the m and the n for respect, what's that respect to?
Oh, the overall equation.
Okay.
So you say third, like in that example we just did, it would be third order overall.
Okay.
Okay. K is your rate constant. The value depends on the reaction, temperature, pressure, presence of catalyst. The faster the reaction, the larger that K value is going to be. Okay. So, and the units on K matter, or the rate. Usually it's like a separate point on your calculations. Okay. So the order of the reactants is based on the exponent. So here we have first order with respect to A, second B, third overall in that case. Okay?
So you write them in that order?
You typically, well, if that was coming from an equation of A plus B, you typically write them in the order of the equation that's given to you, but it's not a big deal if you reverse that.
So you could say second order B, first order A.
Yeah. You could, it doesn't, it's like 4 plus 5 is 9, and 5 plus 4 is also 9, so it doesn't really matter. It's just people usually just do it in the order of the equation, but it's not wrong if you don't. Okay? So the units of K can be calculated by the reaction order. Okay? Usually the units for K are a separate point. You get 1 point for the value, 1 point for the units. Because especially when you start getting second and third order, your units get a little more complicated. Okay? So if we were doing that one, K would be equal to rate over A, B to the second power. And so when you put in just the units, no numbers, you put in just the units, you would get mole over liters per second, mole over liter, and then mole squared over liter squared because of that too. And then what would cancel out? You would get these and these to cancel out, so then you would have that as your unit. Okay? But I want to show you how you'll often see this written in the exam, is they don't like to do the over thing, I guess because of the way it types in. So a lot of times you would see that as liter squared times mole to the -2 times second to the -1. I know, but it shows up a lot in AP Chem, so I want to make sure y'all recognize that. It's not a bad idea for you to put your units that way as well. Why to the negative? Because if it's to the negative, where is it really supposed to be? On the bottom. So I want to make you aware of that. But oftentimes, just the calculation, just the units themselves are a separate point. Okay? But there's an easy way to do this, honestly, because of what's going to happen. It's the shortcut way. So if you have third order, everything's going to be 1 less. Like the moles in the liter are going to be 1 less. So if you have third order, you're going to have L2 mole 2. If you have first order, you have second order, etc. If you have a 0 order, it's just 1 over time. Okay, and that's written in your notes. That's just kind of a shortcut. So that's a good thing to just kind of memorize. Or throw the units in there and do the calculation yourself if you want to, if you don't memorize it. Okay? So determining the differential rate from experimental data. That's what we're going to do our worksheet on. Okay? So I'm going to show you the shortcut way first. You do have to know how to be able to throw it in there and calculate it, but most of the time, being able to look at it, you can figure it out. So I'll show you both. I'll show you one way to just figure it out, but I will work out one where we actually put it in and prove it to you if you don't believe me. Okay? But if you are doubling the initial reaction concentration, and you see that your rate also doubles, then it's going to be a first order. Just go with it for now. Okay, I'll show you how, but I'll show you how to solve it, but I'm telling you, when you get to working a kinetics problem on the AP exam, especially if it's a multiple choice, you want to just be able to look at it. I doubled the concentration, my reaction rate also doubled, then it's going to be first order. Okay? If I double the concentration and my rate quadruples, it's going to be second order. Okay? In order to be third order, what would it have to do if I doubled my concentration? Times 8. Yeah. You don't see that very often. It's not very often that there's a third order in respect to a reactant, but it does happen occasionally. Okay? If doubling the concentration does not change the initial rate, the rate stays the same, then it's zero order. It means doubling the concentration had no effect. And there are cases where one of your reactants is going to be zero order.
Wait, what's triple order?
If you double your concentration and the rate times 8 is a third order. I don't think that's written in there, but I was just going to, it does show up occasionally. Okay? So here we're going to determine the rate law. We're going to do it first mathematically, and then we're going to see that it works, that we just say double it. Okay? So when you're looking at this, you want to keep one of them constant. So we have this equation, 2a plus b equals 2c. We don't care about c. It's not going to show up in the rate law. So what you do is you pick two trials and where one of the items is held constant and the other one is changing. So that way you can check for one and then you go and do the same thing for the other one. So in this case, we're going to try to see what order A is. Okay? So if I look at A and I see that trials or experiments 2 and 3, A is double but B is held constant. Okay? So we're going to make our life easier. We're going to put the bigger number on top. It doesn't matter if we do rate experiment 2 over experiment 3, okay? And so remember, our rate law looks like this, right? Rate, I forgot to say that I was writing. I don't want them to, I want that off. Okay? So rate looks like this. And what are we going to be solving? Okay? So first of all, we're going to solve for that little x. So we're going to say, we're going to use experiment 2 and 3. 3 is bigger, so I'm going to put it on top. So I'm going to say rate of 3 is equal to k a x b y over rate of 2.
How did you choose to use 2 and 3?
Because in 2 and 3, I'm doubling the concentration of A, but I kept B constant. Yeah, it's going to make my math a lot easier. So then I basically plug in what I know from the problem. So rate is 0.8 equals K over 0.1, no, 0.2, excuse me, X, 0.4, Y, running out of room, divided by 0.2 equals K, 0.1 X, 0.4 Y. So I can cancel out K, right? Because it's the same on the top and bottom. I can cancel out that. I did not leave myself enough room, sorry. Is everybody with me so far? I'm going to erase this because that's, I already have that written. I need to just do a new page next time. Okay, so now I'm left with 0.8 over 0.2 is equal to 0.2 x over 0.1 x, which gives me what? Well, what's 0.8 divided by 0.2? 4 is equal to, what's 0.2 divided by 0.1? 2x. So what would x be equal to? 2. Now, there's a much easier way to do that. I could have looked at that, right? So I want to show you why this works by us looking at it and saying, hey, I doubled, that shouldn't be 2.
Yeah, is there like
Did I do something, did we do something wrong with the math?
But two squared is 4.
Huh? It should be, yeah, second order. Yeah, second order, that's right. Yeah, because if it doubles, it's first order. Yeah, never mind. Brain. So that x is now a 2. So then that means, so far we know that rate is equal to k, and then a is going to be second order. Now to get for b, we would do the same thing, but now we would use what trial? 1 and 2, and you would do the same thing. I'm showing you, we can do it, but I'm showing you why when I tell you if you double the concentration and the rate quadruples, it's second order. I'm showing you how we get that. So you don't just have to trust me.
Oh, so we don't actually have to work all this out over
No. You should initially right now, when we're doing them, most of the time on an AP exam, they're going to come out to a nice whole number. But there are occasions when you solve for that x and you get an integer other than 2 or 4, or you get a decimal, or you get a fraction. So I need you to know how to do this, okay? And then sometimes you'll get it where they don't hold one constant, and you have to figure it out that way. I'm showing you why when I tell you if I double the rate and it quadruples, it's second order. Otherwise, you just go, well, why? And now you know why, so you can see it mathematically. So without doing it mathematically, what is B going to be? First order, right. And you don't have to put the 1, you just leave it be. So what's the overall order of that reaction? 3. Okay? 3. Okay? All right. But I wanted you to see how you do that mathematically, because I can't send you into the AP exam not ever having calculated, just going based on that. This is the same thing. I wanted you to see that. So let's do this next one. Determine the rate law. So this one's only got, this is just an A to a B, so it's only going to have, so what is the order going to be for, so we know it's going to be rate is equal to K, and then when I doubled the concentration, what happened to the rate? It quadrupled, right? So what makes it second order, right? And you could actually write this as your explanation if you didn't want to go through the calculations. You can say, you can't just write it down. You have to say, because the concentration, when doubled, the rate quadrupled, that makes it second order. You can use that as an explanation, okay? And if you're able to do that, I suggest you do, because that other process is tedious, okay? Now, if you double the concentration and it's not a clear cut double, quadruple, then you will have to do those calculations.
On our test, are you going to give us one that doesn't follow this rule?
On your test? I don't remember what the test has on it right now. I mean, I know there's kinetics on it. I don't remember if there's one like that. I have to go look at it.
Can we do one where it's not like easy?
I mean, if it's a multiple choice question on an AP exam, it's going to be clear cut. It's just sometimes it shows up as a free response, but most of the time it is clear cut.
Okay.
Yeah. Okay, let's look at this one. Determine the rate law. Start with experiment 1 and 2. You doubled the concentration. What happened to the rate? Nothing. So A is going to be 0 order. For B, you doubled the concentration. What happened to the rate? Doubled, so B is first order. So our ultimate equation, you would actually not necessarily write down. The final would be just the B. You wouldn't put the A to the 0.
Can you explain how you know that, like the A0 order?
Because when we doubled the concentration, so we held B constant right here. We doubled A, it had no effect on the rate. So that is 0 order because it didn't change the rate. Because if I doubled the concentration and it affected the rate, then it matters. because there are some things that whatever the concentration of it is, it doesn't matter because it's not going to affect the rate of the reaction. There are some things that are zero order. Yes?
When you're answering it, do you answer it with like a rate equals K or just put a number? Or like,
So, no, you just leave it as B. Because theoretically, I could use any concentrations and plug it in. Then I could solve for the rate for what that is. Right. So now I'm going to, we're going to be solving for K in a little bit.
when I ask them orders, do you give them a number? Like,
If it asks what order it is, yes. So if they, and you just look at what it's asking. So if it said, what is the overall order of this reaction? If it's a free response, they're going to want you to have work to show, and then you would ultimately answer first order. Okay, overall.
and then just like the rate law, then you write out the equation.
Right. If they say, what is the rate law, you would write this out. Okay. You would not put to the zero in there. It's not necessary. It's redundant. Okay. So here's one more. Y'all go for it.
So on the worksheet, whenever it says order of each reaction, it just wants us to say like A has first order.
A, yeah. And you can just write you can just do brackets A and then write out like next to it what their order is.
And that would be the rate law expression.
No, the rate law expression where it says rate is equal to K and then brackets of whatever their exponents are. The whole rate law is the whole thing.
Okay, and then value of rate, that then we have to find the unit.
Yeah, well, you have to also find the value, not just the units. Okay, so here we have what we think it's going to be. We go 1 to 2. That one stayed the same. That doubled, so we have what order? First order, okay? Because 2, 1 is equal to 2, A is first order. What about for B? Yeah, B doubles both. And what happened to the rate? So we know that was second order. Yeah, because when we doubled B, there was no effect. That means B had to be zero order. Because we already knew and already figured out that A was first order, right?
B was doubled and then.
But there was not one where A was held constant. So if B had an order, it would have had a larger effect because you already know it's doubling because of A. When I also doubled B, nothing happened. That means B has to be second order. I mean zero order.
Wait, so
Okay?
they can't double them, they can't both be equal at the same time.
If both of them had an order, both would affect the rate. It's just that so far we've held one constant and been able to check. In this case, B is never changing without A, where A is constant. Okay? Okay? All right, so we're going to determine the rate law, and then we're going to determine the value of K in this one. Okay? So by looking at what's going on here, what do you think the rate law is? NH4. So look at experiment for NH4. Look at experiment 2 and 3.
NO2 first. Second order, no, first order still.
They're both first order?
Yeah.
So now we can't say A and B, we have to say what they actually are.
Yeah, because we have an actual equation, yeah.
Do you not have to do the plus?
I am. I'm trying to fit it in there. I'm running out of room. I'm just going to start this here. Okay, so there is our rate law. And then it says determine the value for K and its units. Okay? So if I'm determining K, it's going to be rate over NH4 plus NO2 minus. Now, it doesn't matter which one I pick. I'm going to pick one of the experiments and plug in the data. It does not matter. Typically, just pick the first one. Okay? You don't have to. You can pick the third one. You just pick one of the experiments and plug it in to get K. Because it's a constant, theoretically, it should be the same for all three. Correct? Yeah? So we're going to have 1.35 times 10 to the negative 7 moles per liter over...
But we get a calculator for this, right?
Oh, you should, yeah, because that usually is going to show up on a FRQ.
So it won't be multiple choice? Or if it is, it'll be easy?
Yeah, it'll be easy. Okay. So do, huh? Should it be what? Oh, per minute. Yeah, sorry. Forgot the minute. My bad. Okay? So you do that math, and let's just do the value of K right now.
It's just 1 over time.
No, this would be a free response.
1 over time.
Is it 0.00027 and then 1
Or no, it's second overall, right?
Okay? So it's second order overall. Well, basically, this is going to cancel, and this is going to cancel, right? Yes?
Yeah.
So we're going to be left with, and I'm going to do it as liters, mole minus 1, minute minus 1.
So whatever you're figuring out is the overall order.
Yeah, so overall order will dictate those
Overall is
units.
seconds
Yeah.
per meter per
Be
minute.
careful with time, because you might assume, like a while ago we assumed seconds and it was minutes. And be careful with time. They like to change that. It can be seconds, it could be hours, it could be minutes. So just be careful with time. Don't automatically put down seconds when they gave you minutes or hours, because then you would miss that point for the units. Okay?
Is this the time when we can just look at this thing and be like,
Some of them
one
you...
less?
Yes, yes. So that was second order overall. So our units on moles and liters are going to be 1 less than our overall order. So, and then if it was 0 order, it would just be 1. It would just be time to the minus 1. Whatever your time is. Don't write time. Write down seconds, minutes, or hours. Okay? This is just them working the problem. I think that's the end. I think we start integrated there.
What's determine the rate law? And justify
You
it?
just did that.
We just did that. That's just another example. Okay?
What's the rate law?
Well, let's look at it.
Rate equals.
Is that the K plugged in and then NH4 plus?
Oh, no, these don't double, Ms. Parker?
Yeah, they do.
Yeah, they do.
You sure?
I mean, going from 10.1 to 19.8, isn't that pretty close to doubling?
10 times 2
Are
equals
we allowed to do that?
Yeah,
Ball?
that's kind of a leap sense.
Yeah, there's a little bit of leeway in there. Absolutely, yeah. I mean, most things measured aren't exactly...
More acid.
I mean, if you don't believe it, plug it in and calculate it. Like, do that calculation I showed you, that how they're actually doing that. Okay? So if I go... I'm going to pause this.
It's around 4.
That one quadruples from 1 to 3.
So how did I get these answers? So we're going to look at first experiment 1 and 3. And I see that I quadrupled the rate. And when I quadrupled the rate, it went up by 16. Okay? So when it went up by 16, if I quadrupled it, 4x, let me change this, 4x equals 16. So that means x is going to have to be equal to 2. So that gives me a second order for A. B is a little bit more complicated because B, nothing on A is ever held constant. So I'm going to look at experiment 1 and 2 because in experiment 1 and 2 right here, we have B doubling, but we also have A doubling. Okay? So then what happens is I have still going up by 16. So roughly half of that 16 times 4 is coming from A because we know that A is second order. So that takes care of half of that 16. So the other half of that 16 for the quadruple would be that it went up by double. okay? So then that would make B second order, okay? So that's how that works. So, or basically you could look at it like this. 2 times 2 is 4, which takes care of that 4 from that quadrupling, and we saw that it went up by 16 times, okay? If that doesn't make sense, you might want to ask me about it in class. So our rate law becomes rate is equal to K, A squared, B squared, or to the second power, rather. So that would give us a 4th overall order. To calculate K, we're just going to choose experiment 1, plug in the numbers, making sure that we square both of those concentrations, and we get 0.0121. And then when we look at our units, we're going to cancel out, and our units would be, remember they're always 1 less than the overall order for the molarity. So we'd have liters 3, moles times 10 to the 3, and then second to the minus 1. I want to caution you when you're writing seconds to make sure you write S to the minus 1 and not SEC. SEC is not an acceptable unit in chemistry for seconds, okay? And that's where we're going to stop today.